Hello, this is Mrs. Taylor, and I'm going to demonstrate how you can determine continuity and differentiability of a piecewise function. So this problem is from the worksheet that we worked on in class today. It looked like this. It was made by Stu Schwartz, posted online. And the directions for the problem is for each function f of x, show work to determine whether the function is continuous or non-continuous, differentiable or non-differentiable, and sketch the curve. Show work necessary to prove your statements. So for A, we have f of x equals x squared when x is greater than or equal to 0, and x when x is less than 0. And in order to determine continuity, we have to determine if each piece of this function is continuous on its own, and then if the functions meet at the same y value for x equals 0, the x value that separates the two pieces. So the proper way to determine if they meet, and by proper way I mean notation-wise, is to you're going to substitute 0 in for x, but you have to be careful with your notation. So what we're really trying to determine is f of 0 is if f of 0 is equal to the limit as x approaches 0 of f of x. That's continuity, that the function is defined and that the limit is the same as the defined y value. So f of 0 would be plugging in 0 to x squared, because x is greater than or equal to 0 for x squared, and that would be 0. And then the limit of the function, well, technically it would be the left-hand limit and the right-hand limit would have to be equal in order for the limit to exist. So notation-wise, this is what I'm doing officially. I know in class we just got in the habit of plugging it into both and see if they're equal, but we need to be more dedicated to writing out the proper notation, because that's what they'll look for on your tests and exams. And so from the left, that's x is less than 0, and so if I use direct substitution, I get 0. And then from the right, that's when x is greater than 0, and so if I use direct substitution here, that would be 0. So the limit itself would also equal 0, because the right and left hand limits are 0. So all in all, our f of 0 does equal the limit as x approaches 0. So that means it's definitely continuous. Okay, so the question is it differentiable? Let me shrink this down. And so differentiability, remember, you use the left and right hand derivative. So what this would look like is the limit as h approaches 0 from the left, f of x plus h minus f of x. And now that I'm thinking through this, we're looking at the derivative at x equals 0. So instead of using that notation, let's make it specific to our point. So a plus h. Ooh, you can't read that. Let me try again. A and f of a. So this is the definition of derivative at a point. And we have a definite point here. X is 0. So when I plug everything in, it looks like this. Limit as h approaches 0 from the left. I apologize for my handwriting. And it would be f of a plus h. A is going to be 0. So the way I write this out is 0 plus h in, and we're going to use f of x equals x because it's approaching from the left. And we're looking at the left-hand derivative. So that would be 0 plus h minus f of 0, which is 0, over h. And then what happens is 0 minus 0 is of course 0, and h over h reduces to just 1. So my left-hand limit is 1, and so that means my left-handed derivative is 1. So the slope approaching 0 from the left is 1. Now, to the right, and I'm basically, I always write x there. I am basically trying to do the same thing as I did up here, but with x squared because we're approaching from the right. So instead of just 0 plus h, it would become 0 plus h squared minus f of 0, and from the right that would be 0 squared, which would be 0 over h. So here, instead of having an h over h, I have an h squared over h. So that reduces down to h. So through direct substitution, I get 0. So algebraically, when I'm trying to determine differentiability, I look at the left-hand derivative, and so we use this limit definition, and I look at the right-hand derivative, and that would be this limit notation, and I see if they're equivalent. If they are not equal, that means that it's not differentiable at x equals 0. So, can't be both, or differentiable, or neither. So basically what we have is a continuous function that's not differentiable at x equals 0. And remember the direction said sketch, so sketch means it doesn't have to be a beautiful graph, but you know, we can plug in some points and make it at least accurate. So for x is greater than 0 and equal to 0, we have x squared. So if I plug 0 in there, I get 0. If I plug 1, I get 1. And 2, I get 4. And we all should know that that is a parabola. And then for less than 0, it's just equal to x. So when it's negative 1, I have negative 1. And negative 2, negative 2. And hopefully you know that that will be a linear function. So from the left of x is 0, I have this straight line. And then to the right, I have a parabola. And so visually, we can see that I have a corner here. However, it is a sketch, so it's obviously not all that beautiful. But you could have also used your calculator to kind of get an idea of what these look like. So that would be how you would complete tasks like the ones on your worksheet, asking you to determine if a function is differentiable or continuous, and show work to prove your statements.